I'm gonna start recording and let me just share my screen and get started. Okay, so where's my pen? Okay, I have to get these. Okay, so let's talk about internal resistance. Okay, so it's been a long time since we last studied these topics. I'm going to start from scratch. Is that okay with you?
Yeah, that's perfectly fine.
Okay, can you see the book as well?
Yeah, I see it. I see it.
Okay, so what what the book says and what the concept of electric internal resistance is. Internal resistance is basically the resistance that is unwanted. The key word here is it is actually unwanted resistance. So what does that mean? That unwanted resistance, what does it mean? It basically means that we don't need to we don't need internal resistance, but it is there only because we keep using batteries. We have power supplies with like cells and batteries. They just produce this internal resistance. But the key word here is that it is unwanted. Okay.
Okay.
So let me just read the book. So such as battery always have an internal resistance. As the current flows through the power supply, the internal there is a potential difference that leads to electrical energy being transferred to thermal energy. Okay, so cannot, obviously it cannot be measured to use electrical characteristics. Okay, so here's the thing that internal resistance can be either low and it can be high, or it can be anything. Okay, it's not a fixed thing. So the number one thing about internal resistance was that it is unwanted. Number two is that it can be either low, it can be either high, which means that sometimes we can say, okay, the internal resistance is very low. We can probably ignore that. But sometimes it can be very high and we cannot ignore that. Do you get the concept?
Wouldn't it be a problem if it was very low? Because then like more current can flow through, more electrons can pass through, and then that would make the wire like very hot, making it dangerous.
Yeah, but just consider this that uh, the we talk about the drop in potential difference. If they're if they're like if the battery is connected in parallel, or if the battery is connected in series, that changes that concept. But the point is that we need to consider that low and high phenomena.
Okay.
So so the point being that it can be either low, it can be either high, and it can just it just changes. That just makes it necessary for us to account for this internal resistance. We need to make sure that we have covered, we have calculated, and we have accounted for all the resistance that there is. Understood? So we need
Okay.
to uh, figure out or figure out a way to account for internal resistance, which by the way is written by epsilon. Okay,
Okay.
so must be the same. of the, there are two potential differences. Okay, the current I can be measured directly using the meter. Okay, so here's the way to do it. Let's let's talk about this way. Okay, so how do we? Sorry, this is not epsilon. I wrote this incorrect. I read this incorrect. How do we measure internal resistance? Because we're studying this only because we need to figure out a way, because this internal resistance, as I said, is unwanted resistance, and it's mostly in the battery. So if you have a battery, a double A, triple A battery, you cannot just you cannot just attach a voltmeter around it and just measure how much it is, how much the voltage is being it's taking. So what we do is we uh, we make a circuit which has a battery, and then we connect that to an ammeter, which the circuit also has a resistor, so it can be a light bulb or it can be anything. And okay, so is that's like a pretty normal circuit. So
Yeah.
what we do is we attach a voltmeter to we attached a voltmeter to actually calculate, actually just find out the number, the electromotive force, the potential difference that's being taken by this resistor. Okay, so here's the thing. This is the total amount of electromotive force that this battery supplies, and the what we find is only some of it is actually used by this resistor. Since there isn't any other resistor, so there shouldn't be a drop in this potential difference. So we say that this potential difference drop is caused by an unwanted resistance, which is basically the internal resistance of this battery. So this is actually inside this battery or cell, whatever. Okay. Okay. So this I
Okay.
is basically the total current in the circuit, and this, since this is in series, it doesn't change. So uh, this electromotive force, this is the total electromotive force that this battery supplies, and this is divided in the potential difference that is given to the resistor, and the sum of it is taken by the internal resistance, which is basically represented by, sorry, which is taken by this this R. Okay, so this is actually the internal resistance, and I is the current. I'm sorry, it's I R, and it can be confusing, but it's actually I multiplied by R, just to clarify. Okay,
Mm-hmm.
so that's basically the concept that is there of internal resistance. Do you understand?
Yeah.
Okay, so Okay, so now how do we set up an experiment, since obviously we need to study that as well. So here's a way to actually set up an experiment that we can actually find out this internal resistance through an experiment where we have different data points and we plot graphs. So here's how you do it. So there are four variables in this four things that are a part of this experiment. So the first thing is the electromotive force. The second thing is the V, which is the potential difference across resistor. The third thing is the current in the circuit. And the third thing is capital R, which is the internal
Resistance.
resistance. Okay. So the thing is that for my easiness, I want to draw a graph that only has two two unknowns. So I want to make design an experiment which has among the four things that are here, two of them should be constant, two of them should be varying. So what I do is I use the same battery throughout the same experiment. So I'll be using, say, a 3 volt double A battery or something. So I use the same battery. By using the same battery, what I do is I make sure that the electromotive force that is supplied to the battery, this, and the internal resistance of the battery, this, they both remain constant. Okay.
Okay.
So the electromotive force and the resistance, internal resistance, they remain constant. Now, how now this potential difference across resistor and this I are, which is the current in the circuit, is actually changing. And how do we change that? We make the
A variable resistance.
yeah. So what we do is we make an experiment in such a way that we can change. We probably have a variable resistor so that we can change the potential difference across this resistor by changing the values of R, by changing the resistance of this resistor. By changing the value of this resistor, I'm changing the potential difference that is across this resistor. So this means that this experiment will be
Wouldn't
giving.
it be better to have the variable resistor outside rather in series rather than in parallel?
Oh, it's actually in the series. The potential difference is actually measured this way, and so it's actually connected to the battery in like the single series. Like, are you saying that I should attach the voltmeter in series because that is
No. The voltmeter is always in parallel. I'm saying
yes,
that you add you keep that resistor, but then you put the variable resistor in series.
yeah, variable resistor, isn't variable resistor in all already in series?
No, as in like another variable resistor.
So
No, so where you have the variable resistor now, you change that back to a resistor, and then you add a variable resistor in series.
Oh, I get it. So you're saying that you can do, so this is a variable resistor
Hmm.
and this is a fixed resistor.
And then the resistors in parallel.
Yeah, so these are in parallel,
Yeah,
and sorry,
no, it's fine.
and this voltmeter is in parallel, and I can just like do this. Is that what you're saying? I'm sorry, just
No, it's like an individual circuit, obviously. It's not
yeah,
joined
yeah,
with
yeah,
the other.
yeah. This is an individual circuit. I'm sorry
Yeah,
that it just less space. Sorry,
yeah.
sorry about
All right.
that. So I get your point. Yeah, that is also a possibility because like, but the point is that we're changing the values of V and I to design an experiment that gives us data values of that gives us these data values. So I'll have a set of values for V and a set of values of I. And what I will be doing, I will rearrange this equation by V is equals to minus Ri. So sorry, minus Ri plus V. So this what this will give is this will give me a graph which has I on the x-axis and V on the y-axis. On the y-intercept, I'll have the total electromotive force that is being applied to the circuit by the battery and a negative gradient graph. Okay. Now, my
Yeah,
question,
carry on.
hello, yes.
Yeah, carry on, carry on.
So now my question is, looking at the equation of the line and the graph, what do you think I'll get by calculating the gradient of this line?
The electromotive force.
No, the gradient of this line. So this is the line. So this is y is equals to mx
Yeah, I know
plus
that.
c.
Uh,
So the gradient of this line is actually R, which is the internal resistance of the battery.
okay.
Okay. So
Yeah.
what I will conclude is that internal resistance of the battery is equals to minus the gradient minus the gradient of the graph. Okay.
Okay.
Uh, is this thing clear? Is the whole experiment clear?
Um, I don't get how the gradient represents internal resistance.
Okay. So we do you get how we made this equation? So we said that the electromotive force is basically the total volts that is basically supplied that are basically supplied by the battery, and this V is the potential difference that is measured across this variable resistor, and
Mm-hmm.
the rest of the electromotive force is basically taken by the internal resistance of this battery. So we concluded that the total electromotive force supplied by the battery is actually equals to V plus I times R. And
Mm-hmm. And
where
I is the ammeter, right?
I is the ammeter, yes, the reading ammeter reading.
And then R is the internal resistance.
Yeah.
Okay.
Okay. So
Yeah,
ammeter
yeah.
reading. So V was the voltmeter reading. Now, the experiment was designed in such a way where I was using the same battery that kept the electromotive force and hence the internal resistance constant throughout the experiment. So I could, I could change the values of the resistors of my variable resistor to get different set of values of V and I, so that so that I can get a data set sort of here, which gave me a graph like this with a negative gradient, obviously. So I concluded by rearranging the graph and actually deducing which of my variables, which of my constants are actually gradient. I concluded that the internal resistance of the battery is actually equals to the minus negative of the gradient of the graph. Is this thing clear?
Yeah.
Okay, so you get this relation. So V is equals to minus R times I plus epsilon. So this basically is a rearranged form of this equation. I'm sorry, I think
Yeah,
it
yeah,
was,
I get it. I get it.
you
Yeah, I
get
get
it?
it. Yeah.
So, okay.
Uh-huh.
Okay, so I think this is I think the most of what internal resistance is there. So that's probably the whole topic of this. And hmm, yeah. Okay, so what else did you wanna study?
Let me just pull it up. Potential dividers.
Hmm, excuse me, I'll just get a glass of water, please.
عباد الرحمن. Whew.
Okay, so can you hear me, Yusuf?
Yeah, yeah, I can hear you.
Okay, so potential dividers is basically something it has something to do with changing the potential difference across a circuit. So sometimes in a, let's say in a, you've seen like a fan dimmer or a dimmer, which basically controls the brightness of the light and or the speed of the fan or something. So what that thing is basically doing is actually controlling the amount of potential difference, amount of the volts that the fan or it's getting. Okay, so what potential divider is basically is potential divider is potential divider is basically something that controls the amount of EMF or potential difference supplied to the circuit. So what basically is that the thing that is common about the potential dividers is that it is a three component circuit. So it's like like a normal circuit, but it has three components to it. The first one, obviously, being the battery. The second one being the resistors. The second and third being the resistor. So, hello, are you
Yeah, yeah,
listening?
I'm here. I'm here.
Okay, yeah, just
Yeah.
keep saying yes or no because
All right.
it's
Okay.
kind of like okay. So the first thing is obviously the battery.
All right.
The second thing is a fixed resistor, and the third thing is a variable resistor.
All right.
Okay,
Yeah, I get
so
it.
three component circuit. What it does, it actually controls the EMF that is supplied the to the circuit. So okay, so this is like a normal diagram of this. So this is the battery. This is the battery which is supplying the electromotive force. This is the fixed resistor, and there is a variable resistor. So I think when you were giving me an example and you were discussing about the this experiment, you were giving me an example of a potential divider where you said we can actually have a fixed resistor or variable resistor in series to this rather than just having a variable resistor.
Oh, oh, all right. I think that's why I got confused.
Yeah. So the potential divider is the circuit which you were talking about, which has like this battery, battery, and it has two resistors that are actually attached to this circuit. The one resistor is actually a fixed resistor, and the second one is actually the second one is actually the variable resistor. Is it clear?
Hmm. Yeah, yeah, I get it.
So okay, so this is R1 and this is R2. This is V1 and this is V2. Basically, there is this whole math which says how you can actually calculate the how is actually doing that. Okay, Okay. So let's suppose this is the fan that we need to slow, or we need to increase the speed, or it is a light which we want, which has like a variable brightness, and this is actually the dimmer. Do you know what a dimmer is? Do
Yeah,
you
yeah,
have it
I know.
back in
I've
UK?
seen one before, so
So
yeah,
like
I've
if
seen one.
you've been in
Like you
Pakistan,
can turn it and then it turns down the brightness or turns up
yeah,
the
it
brightness of the light.
turns down the brightness, or okay. So let's see. Now we want to control the speed of this fan or the brightness of this light. Now, okay, just concentrate on this equation. So this is the total voltage. Epsilon is the total electromotive force that is being supplied to this. And electromotive force is equals to I times R. Okay, so V is equals to I times R. And so, and what is this R? This R is basically the total resistance of the circuit. So
Okay.
this RT is basically the total resistance. Now, since these two resistors are in a series, we can just say that they are RT is the total resistance of the circuit is R1 and R1 plus
R2.
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 Okay, so the current is actually equals to epsilon divided by RT, which is actually equals to epsilon divided by R1 plus R2. Is it clear?
Mm-hmm.
Okay. Now, what's this V1? V1,
That's the voltmeter above R1.
yeah. So
Is it
V1
like
is,
V is it like V total equals V1 plus V2?
yes. Yeah, exactly. So V1 plus V2 is equals to epsilon. If we consider there is no other internal resistance in the battery, we can say that this is the total electromotive
Oh
force,
yeah, negligible internal resistance.
negligible internal resistance. I'm sorry. So V1
No, that's
is
fine.
actually equals to I times R1. Okay.
Wait, can you repeat that again?
So since
Just repeat it because I didn't hear it properly.
okay, so V1, which is the voltmeter reading around the resistor one, which is our fan, is equals to I, which is a constant current in the circuit, times
Mm-hmm.
R1, which is the resistance of that fan or light.
Oh
So
yeah, V equals IR. There you go.
yeah, so that's simple. Okay. Now, what happens? Now let's see what happens when I substitute this thing. When I substitute this whole thing in place of when I substitute this whole thing in place of I. So V1 becomes equals to epsilon R1 divided by R1 plus R2. You get it?
V wait, V1.
So I've actually plugged in this I is equals to epsilon upon R1 plus R2 in this equation. In this equation.
Could you
Do you want me to repeat?
could
I'll
you
just say that because
yeah, can you please repeat it?
okay, let's do this simply. So in place of this I, since this is constant throughout the circuit, since this circuit
Uh-huh.
is a series circuit,
Yeah.
we can write in place of I an expression which we deduced just a step before, epsilon upon R1 plus R2. Can I write, because this thing, like we've already proved that I is actually equals to epsilon divided by R1 plus R2.
Yeah.
Yes?
Yeah. We've done that.
So in place of I, we can write epsilon divided by R1 plus R2. We can just substitute this whole equation in this equation.
It's like, because RT is R1 plus R2. Oh yeah. There you go.
Okay.
Yeah, I get it now. Yeah, I get it. And then you just do R times the electromotive force.
So this is electromotive force divided by R1 divided by R1 plus R2. Okay. Now,
Yeah.
okay. Now now check this out. We have now we have one variable v1. V1 is a variable and R2 is a variable. Other than that, epsilon and R1 are both constants. What does this suggest?
Right, V1 and R2.
This suggests,
I mean, isn't V1 is just the voltmeter, like it's just measuring the potential difference.
yeah.
R2 is the variable resistor, so you can change it,
Mhm.
and then electromotive force is just the it's just it's just like the total resistance, isn't it?
The electromotive force is basically the total volts in the battery. So it's like a 6 volt battery or like a 240 volt,
Oh,
240 volt power supply in your house.
so how is oh wait, yeah, so electromotive force would be a constant, and then R1 is like is like is wait, so how is R1 a constant?
It's a fixed resistor, so it cannot be changed. We cannot change our.
Oh, okay. All right. Wait.
Okay.
Yeah.
So this suggests that V1 is actually dependent on R2. V1 is dependent on R2. Okay.
Yeah.
So what does this suggest? The
Yeah,
resistance
yeah, I
I,
get it now. Yeah, V1
the
is dependent on
resistance
R2.
I set of the dimmer actually controls the speed of the fan on the brightness of the light.
Yeah,
So
the
what
variable resistor.
exactly? So the resistance of this variable resistor is actually controlling the potential difference that is across the fixed resistor.
Uh-huh. There you go.
Okay. So
Yeah.
that's how actually that's basically the math. That's basically what do you want to call it? The thinking, the thought process of behind that small device dimmer at your house.
Wait, could
What
you scroll down a tiny bit? I want to see what you've written there.
so
Yeah.
there?
V1 is dependent on R2. Could you say could you write because R2 is a variable resistor?
Yeah, sure. Because R2 is a variable. Like it's we can change it. R2 is like an independent value.
Mhm.
So if we want
How R2, how V1 is dependent on R2. I mean, V1 is just recording R1 and then R1 is just a fixed resistor. So wait, so how is V1 dependent on R2,
okay, so
in general?
That's the whole point
Like I know that R2 is a variable resistor and you can change the resistance, but like V1 is recording a fixed resistor, you know.
Mhm.
So how is V1 dependent on R2?
So the thing is that V1, yes, V1 is only measuring the potential difference across R1, but what it's also doing, it's also measuring the volts, the electromotive force that remains in the circuit after R2 uses it. So the total elect
Oh,
so R2, it's V1 is
wait, could
not.
you write this down, please?
So R1 is not only measuring R2, sorry, V1 is not only measuring R1, it also is measuring what is left after R2. Okay,
Yeah.
does it make it clear?
Yeah, I get it. I get it.
You get it now?
Mm-hmm.
All right. Do you have any questions? So this is like the uh, total theory behind the potential divider, and this is like what a wire potential divider looks like. It was I've seen something like this in my science lab, and I think you must have seen it as well.
I've seen a variable resistor, just not like that. It's a lot smaller.
Oh, okay, no, it's just like a very old thing, but it's still like used to teach. But okay.
I mean like the variable resistors that are in like fans must be tiny.
Hmm.
Yeah.
So it's like
That
a
would never
different
be
thing.
that big.
Oh, obviously, yeah. Like you wouldn't like want this big thing just to control the speed of your light. It's like
Yeah.
very different from.
Uh-huh.
Okay, so there is a use of potential dividers as sensors.
Yeah.
Let's read through this.
You can use them on like
Yeah.
you can use them on like you know those lights that turn on in the dark because you know it's dark.
Mm-hmm.
Yeah, it's like once it reaches a certain light intensity, they will
Yeah.
let the variable resistance will turn the resistance down so that more current can flow through and stuff. So scroll up. Sorry, wait, I'll tell you when to stop. Yeah, stop. So you see where it says you see the LDR sign.
Yeah. LDR
Yeah,
sign.
yeah, the right where your pen is. You know that graph where it shows resistance and light intensity. That's what I was talking about.
Oh yeah, yeah. That's yeah. So I think that's all there is with the potential dividers as well. So
Yeah.
just to recap, so in place of this uh, resistor, we can this potential in place of this variable resistor, if I make an if I place an LDR, so it's LDR, obviously you mentioned, is
Uh-huh.
a resistor which controls the resistance with respect to the light intensity. So it's
Uh-huh.
obviously an inverse relationship. So
Uh-huh.
this is the resistance, and this is the light intensity. So if light intensity is too high, the resistance gets too low, and if it's too, the light intensity is like too low,
Yeah.
so the resistance gets.
This is a graph for an LDR.
Yeah. So this is the graph. That's the graph. You're right. So
Can we do like a short can we do like a lesson tomorrow? It may not last an hour, it may last like 30 minutes or 45 minutes, but it's just like me going through questions with you because I have a test.
sure, yeah, we can do that.
Oh, okay, thank you. I
Okay.
think it's the end of our time. Wait, no. Yeah, it's the end of our time now.
Okay. Yeah, I was just finishing things up. So
Uh-huh.
make sure I just send this over to you, this whiteboard to you on our WhatsApp group, and you can
Uh-huh.
probably go over this math. So I know it's like a bit. I try to explain it on my own board, but you can like find this in the book as well. So
Yeah.
if you
I
wanna,
have my own resources, so it's not all bad.
yeah. So if you want to use them, that's fine as well. The point is that you should have the correct, you should have like a strong concept. So I think this is gonna be it for today. If you have any questions, you can ask them now. And
No, I'm fine, thank you. Mo mo
and
mo most of my questions will be tomorrow.
oh yeah, yeah. Okay, so I'm looking forward to them, Yusuf. It was nice talking to you today, and I'll see you tomorrow. Okay.
Okay, assalamu alaikum.
Walaikum assalam.